Okay, so I guess we should get started while people are still walking in. So welcome everybody to the tutorial on statistical learning theory, which is going to be led by John Shaw-Taylor and Omar Rivas-Plata. I guess John Shaw-Taylor doesn't really need an introduction, but I'll quickly introduce him regardless. He's a professor and the director for the Center of Computational Statistics and Machine Learning at University College London. He has been doing research on a wide range of topics, starting from graph theory, cryptography, work on neural networks, but I guess he's most well known for work on kernel methods and support vector machines. He has published over 300 research papers and 2 books on support vector machines and kernel methods. He's also been very influential in fostering and bringing together the research community in Europe on machine learning. He has founded the Pascal network, and he has also, I've been told, founded actually the Eurocode conference, which doesn't exist anymore, but through its success has forced the code community and the code conference to become more international and to move out of just being a purely US-based conference to now be a more international, also European conference. Omar Rivas-Plata is currently a PhD student at University College London. He has already earned a degree in mathematics, actually, from the University of Alberta, where he has started to work with Csaba Csefesvári, who he is now also currently working with at DeepMind. So he is both in academia at UCL and working as a researcher in DeepMind. Maybe last but not least, I've been told that John's father was a racing car driver, and that is very noticeable if one ever gets a ride with John. So let's see what happens if we hitchhike with John.
Thank you very much. Thank you, and thank you for showing an interest. So, statistical learning theory, Hitchhiker's Guide. So I'm going to start with a look at a kind of overview of why and what the aim of statistical learning theory is. So I want to just start with a plot of 2 distributions. These are distributions for 2 different algorithms, a red algorithm and a blue algorithm. And what they plot are the generalization errors, so the test errors, as a random draw is made of different training sets. So you can imagine you've got a problem you're trying to solve, and you generate random training sets. You run your algorithm on the training set, and you find out what test error it has, and then you do it again and again, and you create a distribution of the performance of the algorithm as that is the random variable, and this is the distribution of that random variable over many, many draws. And I think if you have a look at it, I've also plotted the mean of the 2 distributions. So this is the mean of the blue distribution. This is the mean of the red distribution, these 2 different algorithms. And they look pretty similar. But I think you can already see from the plot that actually these algorithms are not so similar in terms of the potential performance that you might get when you run them on a particular training set. Remember, we only have 1 training set. And if we want to look at the kind of worst case or sort of, tail of the performances we might expect if we were to run this algorithm on a real data set, the blue algorithm comes out at a 95% confidence at that test error plotted there, while the red algorithm is significantly better. So in fact, these 2 plots are made for a Parson window algorithm, just taking an average of the positive, average of the negative, and drawing a vector between them, so it's a linear function, and it just is very simple. And the second is a linear SVM, so they're actually learning with exactly the same set of functions. The algorithms differ only in the way they choose the function that they use from the training data. So I think what I wanted to draw from this plot is a few kind of key observations about the motivation for statistical learning theory. So what is a learning algorithm doing? For a fixed algorithm, function class and sample size, the generating random samples, those are the training set, gives this distribution of test errors. And the point that comes out of that plot is if we just look at the mean of that distribution, the mean of the error distribution, it can be misleading. The point being, when we actually run the algorithm, we will only have one training set to use. That will be the data we actually got for training that algorithm. And so the mean of that distribution may not be much use to us. What we want to know is how we perform on our training set. And this is what statistical learning theory is attempting to do. It's looking at the tail of the distribution and finding bounds which hold with high probability over the random sample of training data. So we want to be confident of the performance that we're going to get. In that sense, it's called worst case performance, but I think that term may be misleading, and we'll come back to it in the following slides. So we're similar in sense to a statistical test. We want some sort of confidence level which will bound the chances that the conclusion we have drawn from our data is not true. So the possibility of us being misled. And this has given rise to the acronym probably approximately correct, which doesn't sound very confidence-inspiring. But what it means by that is you have a confidence parameter, and what you want to be able to bound is the probability that you have large error will be less than that confidence. That confidence is that tail bound on the distribution. We want to be confident that we are not going to be having worse performance than the bound is giving us, or the chances of that happening are very small. And hence, we say high confidence bound, the probability of being approximately correct is high. So we're probably approximately correct. That's and if I show you the whole thing again, the bounds here for the Parson window, this is a quite weak performance in the probably approximately correct sense, 0.3 error, whereas the bounds for the SVM in this case are around 0.22 or significantly better. So that's just framing what statistical learning theory is trying to do. It's trying to give us reliable estimates that we can use to perform an understanding of algorithms and also of their performance. So I'm going to now move to an overview of what we would like to cover. I'll be giving some definitions and notation, risk measures and generalizations, some of the definitions that are required. I'll then be handing over to Omar to give an introduction to what we're calling first generation statistical learning theory. So it's worst case uniform bounds and the Vapnik-Chervonenkis characterization of learnability. So this is a sort of a historical context that will then set the scene for the second generation statistical learning theory, which I'll be presenting, which is where we arrive at so-called hypothesis-dependent complexity and structural risk minimization, margin bounds, and the Pack-Bayes framework. And then finally, Omar will then give some ideas about next generation statistical learning theory, looking at stability, deep neural networks, and future directions. So that's the overview of what we plan to cover in this tutorial. We'll try and leave time for questions at the end if we succeed. So things we will do, we'll focus on the aims, the methods, and the key ideas. We'll give outlines of some proofs, and we're aiming at what we're calling a hitchhiker's guide in the sense that we want to give you an understanding of what you can get out of statistical learning theory, how it can help you in maybe thinking about algorithms, thinking about performance and using exploiting the methods that statistical learning theory can provide. What we will not be doing is giving detailed proofs or a full literature, and I can apologize right away to the many, many papers we will fail to reference. We've given a short sort of bibliography at the end, but it is no even remotely attempting to be comprehensive. So please accept my apologies if your papers are not included. We've tried to at least give some starting references for people to link to. We're certainly not going to aim at a complete history, and we're focusing down onto a particular learning paradigm. We will allude to others, but the main focus will be this statistical learning approach. But we're not going to give an encyclopedic coverage of statistical learning theory. So just those are the caveats. Okay, so let me get into this, just introducing some of the notation. So we're thinking of a learning algorithm as being a mapping from a training set, and we're going to fix on M as being the size of the training set. And we're typically thinking of pairs, input-output pairs in the training set, input and corresponding label. In some cases, there might not be a label, but we're going to leave that in there anyway as a sort of standard notation. We're thinking of a hypothesis class, which is a set of predictors, for example, classifiers in the case where the labels might be binary labels. But there are other possibilities, of course. We're expecting to have a training set, which is a set of these pairs, input-output pairs of size M. So it's a finite sequence of input label examples. And the key assumptions that are made by, that we're going to use in this presentation are that there's a data generating distribution, which we're going to denote by P over these pairs. The learner doesn't know what P is and only learns about P through seeing this training data, and it gives insight into P because the training data's examples are generated IID from that distribution. So that's the key link. So we're having to, our test performance will be the performance under that distribution of a randomly generated example on that distribution. But the only access we have to that distribution is through those M training examples generated IID according to that distribution. These assumptions can be relaxed in many respects, but we won't be discussing that in this tutorial. So for example, the IID assumption can be weakened and so on. So we're not going to address that, but just for information. Okay, so the things that we would like to do with a sample is clearly learn a predictor, but also we would like to certify the predictor's performance. We'd like to give some, if you like, certificate that will tell us the performance we can expect. As I said, with high probability, some sort of tail bound will say, okay, there's a chance we've been misled by this training set, but modular that probability, we're expecting this performance. So the two parts, learning a predictor, we would like to have algorithms driven by some learning principle, and they will be informed by prior knowledge that will be resulting in inductive bias, and we'll be trying to understand the effect of that bias on the performance of the algorithm. And this will be giving us the certification of performance, which is really what's happening beyond the training set. So we can clearly observe what happens on the training set, but what we're interested in is how we're going to perform in the wild, if you like, or beyond the training set when we actually run this algorithm on new data generated according to the same distribution. And we refer to that as generalization bounds. But actually, I think we're going to highlight, I hope in this presentation, that these two things interact. A good bound will give rise to an algorithm that optimizes that bound. So it's not that we're just doing this theory for theory's sake, potentially we will translate that theoretical insight into an improved algorithm that will, as it were, drive, as we saw in that case of the linear SVM, an improved distribution of errors and hence an improved performance that we would hope to achieve using that algorithm on the data set that we actually get given. So these are the things we would like to achieve. The measures of performance will always be through a loss function, which is measuring the discrepancy between the prediction that we make on the input with the function h and the true label y. So we have two measures of performance: the in-sample performance, which is the empirical risk, which is basically the average of the loss that we experience on the training data, so the M training samples, and the theoretical risk or out-of-sample risk, which is the generalization error, the expected performance, the expected risk that we would see from a randomly chosen test example. And just as examples of the types of loss function we could consider, the 0-1 loss, which would be for classification, would say 1 if we make an error, 0 if we don't. Squared loss, appropriate for regression. Hinge loss, which is the one that's used in an SVM, and we'll come back to that later, which is some sort of proxy for or intermediate between the continuous loss and the 0-1 loss. And then, for example, we could have a log loss if we were doing density estimation, where actually there isn't a label. So the label there, y, is a dummy variable in that example. So generalization, if h does well on the in-sample pairs, will it do well on the out-of-sample pairs? And the thing that we're looking at in terms of performance is the gap between the in-sample performance, that average on the training set, and the out-of-sample performance, the performance we can expect on new data. And what we would like to have are upper bounds on that, which hold with high probability. And the delta is, as I mentioned already, used to sort of quantify that probability. So delta h being less than or equal to some function epsilon of the sample size and that delta confidence. And that would correspond to a bound, an upper bound on the actual error rate that we would expect on test data in terms of the empirical plus this gap function epsilon. We're also interested in lower bounds, and this is the possibility of getting an estimate of the minimum gap that we can expect. We'll come back to that again later. So flavors of these bounds, we might expect distribution-free, distribution-dependent, algorithm-free, algorithm-dependent, and clearly, you know, there will be trade-offs with the amount of generality that we're able to achieve in terms of the performance, in terms of, the quality of the bounds. Again, we'll be mentioning that later. Okay, so having set the scene in that way, I'm going to hand over now to Omar, who will take you through the first generation statistical learning theory.
Thank you, John. So I would like to start by presenting the easiest possible setting of generalization. It might seem like a very unrealistic, but just for starters, you know, thinking from a very simple-minded point of view. Let's say that we have just one function. That's all that we have access to, one function. And then we're going to use it as our building block to look at the problem of generalization. So if I have one fixed non-data dependent function, a non-random function, and I look at the empirical risk of that function, I look at its expectation, turns out to be equal to the theoretical, to the out-of-sample risk. So in this setting, the problem of bounding the probability that the generalization gap is large turns out to be the problem of looking at the difference between a random variable and its expectation. And that's something that in probability is called the deviation inequality. Furthermore, the terms in that sum defining the empirical risk are independent random variables. That's because of the IID assumption, and because we are looking at one non-data dependent function only. If the function was learned from data, then correlations are introduced, and then this reasoning does not work anymore. But we are looking at a non-data dependent function. So if they are also bounded, if we assume that those functions are bounded, then we can use what's known as Hovden's inequality to bound the probability of having a large gap. It's exponential in the sample size and in the amount of deviation. So the usual trick, probably a lot of you are familiar with this, if you make the right-hand side equal to delta, so for a given confidence parameter delta, you equate the right-hand side to delta, and then solve for epsilon, what you end up with is the inequality below. So with probability at least 1 minus delta, that's what we mean by with high probability, we have an inequality for the true risk, the true but unknown risk, in terms of the empirical risk, which is computable from sample data, and a function that depends just on the sample size and the confidence parameter. So I would like you to pay attention to that frame, to that framed part at the bottom. That's the typical picture of a generalization bound. So scaling up a little bit, another kind of simple scenario, if you have a finite hypothesis class, a finite set of examples from which to choose from, then your algorithm, let's say that we aim for a uniform kind of bound. If I use any function from this class, how bad can the generalization gap be? That means bounded the probability that for all functions in the class, the generalization gap is small. So the tool to use in this case, since we're dealing with a function, with a finite function class, is a probability tool called the union bound, also known as countable subadditivity of the probability measure. So look at the complement. The probability that there is at least one function in the class that has a large generalization gap can be bounded from above by a sum in which all of the terms can be bounded. Just as in the previous slide, we bounded the probability for a single function, and you equate that to delta, then you end up with a generalization inequality, with a generalization bound that holds with high probability uniformly over the finite function class. The size of the function class comes in that inequality inside the log term, and the idea is that for more complicated cases, so if now you want to scale further up and you don't have a finite number of functions anymore, but maybe infinite, maybe countably infinite, possibly uncountably infinite, then that number inside the log, which right now is the size, the number of elements in the function class, that has to be replaced by something different. Ideally, something that replaces the notion of size, how big the class is. Not just the cardinality, because for infinite sets, the cardinality, well, we would have a very uninformative bound on the right-hand side. So the next question is, what if uncountably infinite function class? I'm going to go kind of just describe the main steps of what is done in this case. One approach that's used to handle this case, you use what's called the double sample trick. So you use a ghost sample, an independent copy of the sample. And doing that, you kind of pass from looking at the theoretical error to looking at the empirical error on the ghost sample. Then instead of dealing with a huge space, where the theoretical error lives, you're basically looking at a finite number of possible behaviors determined by the second sample. and then with a union bound, but a clever use of a union bound where the overlaps have been handled in a smart way, then you can end up still with a probability inequality that is informative. A symmetrization trick comes in too, so that one bounds the performance, the probability of having good performance in one of the samples, but bad performance in the other samples. And something called the gross function of the hypothesis class comes in. It basically tells you, for a fixed number of examples, if I have m sample size, and I'm going to use this hypothesis class, how many different labels? Remember that we're looking at the binary classification case. So how many different plus or minus one labels can I do with this hypothesis class? And the VC dimension is defined as the largest sample size for which you can have all possible labelings, the largest possible labelings on m points. So let's have a look at what the upper bounds looks like. What was proved by Vapnik and Chervonenkis is the inequality shown above. It's a uniform bound on the generalization gap. It's uniform over the function class. And what comes up inside the log is now the gross function of the given hypothesis class, of the hypothesis class that you're dealing with. In principle, that gross function can be bounded. It's always finite. It can be bounded by 2 to the sample size. However, if you do that, you end up with a very uninformative upper bound, because the log of the exponential, then the log kicks the exponential, and then you end up with a bound that basically does not depend on the sample size, kind of constant in sample size. Things don't work all that nicely. But fortunately, there is a tool to handle the gross function that says that as long as the VC dimension of the function class is finite, then the gross function can be upper bounded by a combinatorial quantity, a sum of binomial coefficients, and that works for all sample sizes, which makes the gross function be a polynomial in sample size, and then you end up with a generalization bound that decreases with sample size. Turns out that the VC theory kind of characterizes learnability in the probably approximately correct setting, in the sense that, well, first let me mention the bounds that you just, the VC bound, the VC upper bound, is a uniform kind of bound, but it's like in a double sense uniform kind of bound. It is uniform over the hypothesis class. It tells you that the generalization gap of all functions in the class are bounded in such and such way with high probability, but it is also uniform in the data generating distribution. And we have a lower bound that tells you that, there exist data generating distributions for which, with high probability, the difference between the risk and the smallest possible risk in the class is bounded below by a quantity of the same order as the upper bound in the sample size. So there are good and bad things about the VC framework. Let me mention what are the limitations. So the bounds are tight in the sense that we have matching upper and lower bounds of matching order. This is a theory that was developed to analyze the output of empirical risk minimizers. And this is something that applies to uniformly over a hypothesis space. So this is something that is not tuned to a particular function. However, practical algorithms usually do not search, or at least this is what is observed in practice. The practical algorithms usually do not search the whole hypothesis class. As examples, you have nearest neighbors rules, support vector machines, or deep neural networks. So sort of like there is a mismatch between this theory and what is observed in practice. Just to give an idea, I'm going to illustrate this with a picture for FVMs, kind of following up on the pictures that John showed at the beginning. So on the same data set for which those pictures were created, you still run a parsen window. That's the blue algorithm. But instead of a linear SVM, use a kernel SVM with a Gaussian kernel. And turns out that the performance of the kernel SVM pretty much beats. I mean, even in expectation, the error, the test error of SVM is much, much lower. So what does this say? Keep in mind that for the Gaussian kernel, the VC dimension of the space is infinite. So looks like the theory is not being able to say much, or at least the VC bounds are not being able to say much as far as the performance of kernel SVM with the Gaussian kernel goes. So I kind of want to mention this as a case study. Here is an example that has infinite VC dimension. However, the observed performance is quite good. VC bounds don't seem able to explain this. In fact, the VC lower bounds seem to kind of be in a contradiction with what comes out of this experiment. And the question is how to resolve this apparent contradiction. So I'm not going to answer that question right away. I'm going to leave it some motivation for what's coming up after the break, which is not right away. So the point is that the VC bounds are worst case kind of bounds. And the example that you just saw, the graph that you just saw, may be suggesting that, you know, sometimes we may not be dealing with a worst case data generating distribution. And how does one then exploit that? Well, answers will come very soon. For now, what is kind of like the Hitchhiker's Guide summary of the first part of the talk? Well, it seems that the theory is quite nice, quite elegant, and complete. In a way, it's right, but wrong. So it's like a nice topic of conversation, but how do we, you know, how does it match the practice? We don't know. So its practical usefulness, it seems like something different has to be used in order to match theory and practice. And with that, we're going to make a short break of like 5 minutes. That's fine? 5 minutes. 10 minutes. 10 minutes break.
Okay, let's restart. So we're going to begin the second part with this presentation on second generation statistical learning theory. So just to recap, we looked at statistical learning bounds and the fact that they bound the tail of the distribution. That's critical in terms of understanding what they're trying to achieve. And through that, they give what are called high confidence bounds on the performance on test data. And the VC theory gave uniform bounds over a set of classifiers. So you basically get the same bound for each classifier in the class, which motivates, as Omar was saying, the empirical risk minimization. Clearly then, to get the best test performance, you have to minimize the error on the training set, and then the error on the test is that training error plus the gap, which is the same for all of the functions in the class. But the point that was made at the end there was that it's also worst case over the data generating distributions. So it holds for all data generating distributions. And this is, I think, the key weakness that was being shown up by the performance of the SVM. But there seems to be a contradiction because the VC theory characterizes learnability. So there seems to be kind of, we're getting good performance, but hey, you know, the performance can't be good because it's characterized. So what we're going to look at is exploiting the non-worst case distributions. So this is quite a subtle point, that actually those lower bounds depend on particular distributions that force us to make errors. And actually the distribution that we're facing in a real application may not actually be of that worst case kind. In fact, it mustn't be if we're able to perform better. So the bounds then become dependent on the chosen function, and that function is in some way able to give evidence that the distribution is not as bad. It'll mean a set of new proof techniques. So we'll try and give you an overview of the proof techniques that arise in order to deliver these results. And then we'll finish up with the approaches to deep learning and some future directions. So that's what we're going to be looking at in this second half. Okay, so the first, I'm going to start with perhaps the simplest way of making the bounds distribution dependent, or function dependent at least. It's the first step towards a non-uniform learnability. So the way this is set up is we take a set of functions, of classes, H1 up to maybe an infinite countable union of function classes, and perhaps they might have VC dimension dk for the kth in that sequence. And these VC dimensions are all finite. And we imagine there's also a weighting scheme that weights our kind of prior belief, if you like, in that class being the class in which the function will be likely to come that we're learning. And what we would like to have is a bound that holds for each k. We're going to have the bound hold, but with the weighting on the right-hand side. So the probability of being misled is now weighted according to that WK associated with that class. And remember, the sum of the WKs is less than or equal to 1, so we can therefore apply our union bound trick again, and what we have is the fact that with probability 1 minus delta, then for all of the classes and for all of the functions in each class, the gap is bounded, but the gap that we get is now class dependent. So it's uniform, the same gap for everybody in one class, but it will be different for different classes. So this means that the function gap will be a function of the class within which the actual hypothesis that we've chosen lies. So it's a first attempt, very simple attempt, to introduce hypothesis dependence. And as I said, the complexity depends on the chosen function. And it drives, as I pointed out, every bound potentially drives a new algorithm. This drives an algorithm that returns the function that you see here on the right. It's the argmin over all of the functions in all of the classes, the union of the classes, which minimizes the empirical error plus the gap associated with the minimum class that that function, so this k of h is the minimum class which that function is contained in. So we're actually, in way, regularizing, according to the class index, we're regularizing the choice of function that so we're trying to prioritize functions with low indices, but trading that index against the empirical loss. So it's a kind of initial form of regularization. And essentially this idea of, measuring complexity of the function is about regularization. So this leads us to this idea of detecting benign distributions. So the structural risk minimization approach is sort of detecting the complexity of the class that is needed to solve the particular problem. So in that case, it's sort of detecting the complexity of functional complexity that is required for that particular problem. But the problem is that you must define the hierarchy a priori. So in some way, it's a little clunky in the way that you have to set this thing up. And so it's not effective in practice. What we would like is to have more nuanced ways to detect how benign a particular distribution is. And this is where the SVM comes in, which uses this margin measure, which appears to detect how benign the distribution is, in the sense that the data is, if you have a margin, it's sort of implying that there's some region close to the boundary where the data is less likely to actually occur. And that makes it easier to separate the two classes, naturally, because there's a bit of wiggle room in the region between the two classes, and you've got a little bit of flexibility, and it's easier to find that separating hyperplane in that sense. So this is the kind of intuition, and it's actually been formulated into minimax asymptotic rates for a class of distributions with this a definition of reduced margin density by Audibert and Tsibakov. So this idea has been characterized in that sense. But while that's really kind of a very useful insight, it's making assumptions that we prefer not to make, and we don't know whether they are valid to make when we actually apply our algorithm to a particular training set. What we would like to be able to do is have the algorithm automatically detect that there's a benign distribution measured by a margin and exploit that to get good performance. And that's exactly what the SVM does, and we'll be showing how that arises. But more generally, there are other techniques that you can, and other, if you like, benign ways of detecting a benign distribution. And Mario Marchand and myself looked at how sparsity can be used as an indicator of a benign distribution. So this is just to show that there are other methods, other things, and they are examples of what was set up as the so-called luckiness framework, which is showing how you can detect these measures of, if you like, luckiness, benignness of the distribution, and how they can be made, it's essentially making structural risk minimization data dependent. So you don't have to a priori set up this hierarchy of classes that we do with structural risk minimization, but they actually arise from the observations we make during the training of our classifier. So what we're going to do now is use the margin example as a case study. So maximizing the margin frequently makes it possible to obtain good generalization despite high VC dimension, as we saw, the point Omar was making in that plot of the, the generalization distributions for the case where the Gaussian kernel was used. The Gaussian kernel has infinite VC dimension, so clearly, we would not expect the, based on VC theory, learning to be possible. And indeed, the lower bound implies that SVMs must be taking advantage of the benign distributions, since we know that in the worst case, generalization will be bad. We can create distributions that would force an SVM with a Gaussian kernel to make high error. That's the consequence of that theory. The fact that that doesn't happen in practice is because the distributions we experience in the real world are actually, you might not think so, but they are actually very lucky or benign in that sense. So we require a theory that can give bounds that are sensitive to these serendipitous distributions, and in this case we're considering the margin is this indicator of this serendipitous situation or luckiness. So the first intuition about how we might approach this is that if we use real valued function classes, then the margin in a sense will give us some indication of the accuracy with which we need to approximate the function that we're learning. Because if there's a nice margin, then if we are finding a function that's not exactly the function, but close to it, it will have similar performance to the function. So that's the kind of intuition that motivates the first approach. But we're going to actually consider 3 proof techniques, because I think it'll be a nice illustration of the different methods that are arising in statistical learning theory. So the first will be based on this approximation accuracy idea and reduces to something known as covering numbers. So I'll first talk about that, but then I'll follow with, again, using real valued functions, so a sort of similar idea, but reducing to how well the class can align with random labels, and this is known as Rademacher complexity. So I'll talk a little more in detail about that, and even sort of give a kind of sketch of the proof. And then we'll turn to looking at an approach inspired by Bayesian inference, and that maintains a distribution over the function class, and will give rise to what's known as the Pack-Bayes analysis, so a combination of sort of a Bayesian approach in that there are distributions, but a pack analysis, and we're giving approximately probably approximately correct bounds. So that's the sort of the 3 approaches we're going to consider. So I'll start now with covering numbers. Now the proof here follows very much that of the VC bound that Omar described. We replace the test error by a proxy, which is the error we would get on a random second sample. And that now gives us a fixed double sample of data, and we're only interested in the performance of functions on that double sample. And so we reduce suddenly to something we can handle very carefully, and there are only finitely many performances that we might be able to get. Or we can handle the performance that we can get. And what we do here in this case, in the case of the VC, it was a finite set of performance. Here we have actually infinite set of performances, but we think of covering the performances that we can get on that set of points up to an accuracy that is given by the margin. So we've got two M points, the M training points and M test points, and we're going to pick a set of functions that, if you like, characterizes the performance we can expect on that 2M examples up to the accuracy of the samples. So given any function in the class, we can find an element in the cover that matches the performance of that function within the epsilon of the accuracy or the margin accuracy that we're interested in approximating to. So that's the idea of a cover, that we find a set of functions that, if you like, describes the richness of performances that we can expect. We therefore can find in that cover a function that is close to the function that was output by our algorithm. It's within the sort of margin accuracy of the function on all of the points. And so that function actually will have similar performance on the test and training, the first sample and the second sample. It will have similar performance because it's within the margin accuracy, it's giving the same values. So when we threshold, we'll have a very similar performance. And so we can apply this idea of symmetrization, which is basically saying it's very unlikely you'll get poor performance on the first half and good performance on the second. The first half corresponds to the training set, so we're getting good performance on the training set, but poor performance on the training set, but good performance on the test set. And symmetrization just says it's equally likely if you swap those points, and so you would then get a very unlikely if all of the errors end up in one half of the pairing. And then we apply the union bound over the cover. So here we've actually taken functions together that are sort of close in this cover sense, and the effective complexity is the log of the covering numbers. So the critical measure you need to have here is the size of this cover. And this can actually be bounded by a generalization of the VC dimension known as the fat shattering dimension. So this is the outline of this, if you like, first approach to proving generalization bounds for large margin classifiers. So I'll now move to the Rademacher complexity. And that starts from considering a uniform bound on the gap over the class. So if we think about this is the probability, and I've put P to the M here, which means over the M sample. This is our random probability of the sample, that all of the functions in the class have a gap less than or equal to epsilon is less than or equal to the probability that the worst class has, the worst gap is less than or equal to epsilon. Trick here is to, again, use this idea of a ghost sample. So we have the original sample. The gap is the test error minus the empirical in-sample error. But now we use a ghost sample, and the out-of-sample error is just equal to the expected value of the performance of the ghost sample. This is the trick of replacing the generalization error with the performance on a ghost sample. So now if we take the expected value of this soup, remember we're looking at this soup here, take the expected value of that soup of the supremum over the gaps, it's less than or equal to, and this is really just replacing that out part here with this expected value, and then moving the expected value out through the average, and that brings an inequality less than or equal to. So it's less than or equal to the expected value over this double sample of the supremum of the, if you like, sort of gap between the performance on one sample and the performance on the other. So it's a very kind of intuitive idea. And here we again apply symmetrization, but now in this formulation, this corresponds to swapping the elements. And we do that by actually adding in a variable here, sigma I, which is a plus minus 1 variable, which if it's plus 1, it leaves them in the same order. If it's minus 1, it swaps them. And because of the fact that they're drawn from the same distribution, if we swap them, there should be no change in the probability. So the expectation is identical when we introduce this expectation over swapping. And these are plus minus 1 random variables, so that is why those are known as Rademacher random variables, and this is why this is known as the Rademacher analysis. And so now we can actually separate out these two parts, and we actually can take the sum, bound them by the sum of the two parts rather than the difference, and we get twice the expectation of this estimator here, which is basically taking the supremum of the function correlation that can be achieved by the function with random noise. So it's kind of a very intuitive concept here. It's sort of saying, okay, I'm looking at how well I can align my function loss with random noise. And this is known as the Rademacher complexity of the class, this quantity here. So I'll show that on the next slide. I'll just take this final thing here and put it onto the next slide. This is the empirical Rademacher complexity, is the expected value for the given training set. So this is for a particular training set. And the Rademacher complexity is the expectation over random training sets of that quantity. So what we showed on the previous slide was this bound here. The expected value of the supremum is less than twice the Rademacher complexity. Now, there's a couple more steps that are quite straightforward using McDiarmid's inequality. Firstly, to show that the supremum of this gap is bounded by its expectation, which is what we've just bounded, plus the amount that we can change essentially with swapping a single element. This is the sort of McDiarmid inequality approach. And finally, also the McDiarmid inequality can be used to bound the Rademacher complexity in terms of its empirical quantity, this one that depends on the particular training set rather than the expectation over training sets. So combining all of that together, we arrive at the following bound, which is the core Rademacher bound, which says with high probability for all functions in the class, the gap is bounded by twice the empirical Rademacher complexity plus a term that is very similar to the sort of term we would get with a single function that Omar showed at the beginning. So the Rademacher complexity is really capturing the key complexity of the function class. It's this measure here of our ability to correlate with our expected ability to correlate with random noise. So it's a key idea. Now, if we can apply that quite readily to SVMs. So here it is for SVMs. Firstly, we need to measure the Rademacher complexity of the function class. And here, the trick is to use the functions you can generate with bounded norm and with a fixed kernel. So I'm taking kernel kappa and norm bound B, then where this is the bound on the 2 norm of the weight vector. So this is the function class I'm interested in. And the Rademacher complexity of that is bounded by the norm of the norm bound B divided by M times the square root of the trace of the kernel matrix. Okay, so that's, I'm not giving you a proof, but it's relatively straightforward proof to show that. So this motivates controlling the regularizing with the 2 norm while keeping the outputs at plus and minus 1. And this gives the SVM optimization where the hinge loss is used to take the real valued approximation that we're using to classification. And we've had to use the fact that if we apply a function like the hinge loss to the real valued functions, then the Rademacher complexity is only affected by the Lipschitz Lipschitz constant of the function, and in this case, the Lipschitz constant is 1. So the Rademacher complexity, well, there's a factor 2 comes in, but it's roughly the same. Putting all the pieces together, this gives a bound that motivates the SVM algorithm, where we use the slack variables psi I standard notation, and the margin gamma is 1 over the norm, because we've used the outputs to be plus and minus 1. So this is the upper bound on the generalization error. So I've hopefully given you just an intuition about how there's a lot of detail I've skipped over, but hopefully it gives you an understanding. So here, this is the equivalent of the empirical error, the slack variable measurement. So if we were getting perfect separation with a margin of gamma, this would be 0. This is the complexity term that came from the Rademacher complexity, and this is the equivalent of the term we get that controls the likelihood of being misled, which was similar to the term we got with a single function. If we consider a Gaussian kernel, it actually simplifies down because the trace of the kernel matrix is just root m, and so we get 4 over root m gamma. So clearly you can see this is motivating the minimization, the maximization of the margin, minimization of the slack variables, which is at the heart of the SVM algorithm. So this is assuring us that indeed the margin is an indicator of the benignness of the distribution, and that the SVM algorithm is able to not only find a function that is performing well on the training data, but at the same time, it's detecting that the distribution is benign in the sense that there is this sort of low probability region close to the decision boundary. So in the sense of Seebekoff and the bound, the sort of the thing I mentioned in terms of this distribution class of, this is actually a detecting that there is something of that nature going on, but it's not in any sense saying it's in those classes that were defined by Audibert and Seebekoff. It's not saying that. It's just saying that it's actually detecting that it's, in some sense, there is this low probability region that is, and it's able to detect that and find a corresponding bound. So just a few comments on the Rademacher complexity approach. It kind of motivates a general plug-and-play to derive bounds based on Rademacher complexity for other kernel-based, and I mean general two-norm regularized algorithms. As you can see, the Rademacher complexity was sort of characterized by this two-norm quantity, so you can sort of plug that into any algorithm, and typically, you know, kernel-based algorithms do regularize with the two-norm, so you can apply it to kernel PCA, you can apply it to kernel CCA, one-class SVM, indeed multiple kernel learning, regression, and so on. So there's sort of a generic thing going on here. However, it's also applicable to one-norm regularized methods, and this actually arises from a very nice property of Rademacher complexity, that it's actually not changed if we take a convex hull of a set of functions. So if you think of, you know, the functions you can generate, say, with boosting, if we imagine a sort of one-norm regularized boosting, then the actual one-norm coefficients, again, we effectively have a multiplicative factor of the norm, the one norm of that linear combination, based on the Rademacher complexity of the weak learners that we're using in that boosting algorithm. So again, a very nice motivation for using that kind of approach. And for example, a lasso regression would fall into that, or different flavors of boosting, you know, linear programming boosting, or one norm SVM, as it's sometimes called, would fall into this class of functions. So it's a very nice kind of motivator for algorithms in that sense. However, the actual bounds are still in themselves not very tight. So you wouldn't actually be able to, you know, get an idea of the real performance, real test performance. So they motivate algorithms, but I don't think we could consider them to be, you know, if you like, giving us a real insight into the actual test performance of a particular learned algorithm. So what I'm going to turn to now is the Pack-Bayes approach, and this will lead to what I think are some of the tightest bounds that are available, but I think also illustrates some very nice other properties that link to Bayesian learning. So I think it's an interesting study in itself. So perhaps also just to set in context, the progression is all about trying to get further away from the union bound, in the sense the union bound is very weak. We could make it work for finite. When we moved to infinite, we had to kind of clump functions together according to their behavior on a double sample, and we could get reasonable performance, but we're again significantly over-counting, if you like, the contributions of different errors. And the Rademacher complexity similarly overcounts the contribution of different errors. In some sense, they're being counted twice. And the Pack-Bayes framework is able to nuance that a little more tightly, and I think for that reason is able to get better bounds. So without further ado, I'll now introduce the key definitions for the Pack-Bayes approach. So what one has here is a prior distribution over the functions. So you're thinking now, this is a separate distribution. Remember, we've had a distribution up until now on the inputs, or input-output pairs. That's our data generating distribution. So we park that, we're going to have that, we're going to continue to have that. However, we now have another distribution, which is a distribution over the functions. In fact, we're going to have two distributions over the functions. There's the prior, which we're denoting here Q0, which is some initial estimate of the likelihood of different functions. Think of it in terms of the prior in Bayesian learning. And then we're going to have a posterior distribution, which is again a similar function over the distribution over the functions, but now can be informed by the data. So the data can be used to define that posterior distribution, but the data must not be used to define the prior. When we make predictions, we draw a function according to the posterior distribution, and we predict with that function. So each prediction, we generate a random distribution. So it's not the Bayesian average of the posterior, it's a random function drawn newly each time. The risk measures are generated from the risks that we've had before, which are based on an individual function, but now we average that risk over this distribution Q. So here we have the in-sample risk is the average over Q of the risk of the individual functions, and the out-of-sample is the similar average over Q. Again, this is all posterior distributions of the out-of-sample risk. You might be wondering how we're going to handle this, but it works out quite nicely in the end, at least for the case of linear function classes such as the SVM. So here's a typical pack-Bayes bound. This is not now applied in any way. This is just the sort of vanilla bound. So if we fix Q0, so we fix our prior before we see any data, then we generate some random data of sample size m for any delta between 0 and 1 with high probability greater than 1 minus delta. For all posterior distributions, the KL divergence between the in-sample error. Now here you're saying, how can we do a KL divergence? Think of the error as being a distribution on getting it right, getting it wrong. So it's a binomial distribution. And we're thinking of the KL divergence between the binomial distribution associated with the error rate of the in-sample error rate and the out-of-sample error rate. So this is a KL divergence between those two distributions, binomial distributions, is less than or equal to the KL divergence between posterior and prior plus log m plus 1 over delta divided by m. Okay, so that's the form of the bound. And let's now think about applying it to SVMs. So we think of the weight vector output by an SVM. First, normalize it, so divide by its norm to make a unit vector in the same direction. We're thinking here SVMs without a threshold, so think of a threshold 0 SVMs. Then for any m and any delta with high probability, the KL divergence between this in-sample error distribution, right-wrong distribution, and out-of-sample right-wrong distribution is less than or equal to a half mu squared plus log m plus 1. Sorry, what's happened? Okay. Log m plus 1 over delta divided by m. Now mu here, I haven't shown you what it is, but what we're doing is scaling that unit vector by mu. Okay, so we're scaling that up, and we're allowing that as a variable here for the time being. So this will hold for all mu, because mu will just be choosing our posterior distribution. So the idea is that the prior here is chosen to be a Gaussian distribution at the origin with covariance equal to the identity, and the posterior is, as I said, mu times the unit vector output by the algorithm, so a scaling of the weight vector, again with unit variance. So now the KL divergence between posterior and prior is just a half mu squared, the KL divergence between two Gaussians. And here we have actually a way of computing this KL divergence between the, computing the in-sample error which is basically the expected value of the 1 minus the cumulative normal distribution of mu times the margin of that point. So this is the empirical average of this sort of function of the margin. So it's sort of saying, as the number of margin errors or margin quantities goes down, we're actually going to get a very low empirical error. So it's very close to our Xi that we had in the Rademacher bound, but it's a slightly more nuanced version of that. So this is the empirical error. We can measure it exactly with this particular distribution. And finally, the SVM generalization error is twice the minimum over mu of this corresponding bound on the empirical average of this Q mu. Now, so, quite a few things are happening here. Sorry if it's being a bit confusing, but what's actually surprising is, despite the fact that this Q mu is some sort of random classification, we're actually able to bound the deterministic classification. We sort of de-randomize this with this factor 2 to the actual SVM generalization error. So it's basically quite a simple argument that if this thing if the SVM is wrong, then the probability of this thing making an error is at least a half. So we're actually able to get that kind of bound. So putting this all together, what we have is effectively a bound on this, which is implied by this KL divergence. You can sort of invert that based on the empirical error, which is computed by this empirical average, and this quantity here, which is based on. So there's a trade-off between the scaling, which will decrease this error as we sort of scale up the margin, but increase the cost associated with this KL divergence term. But we can choose mu because of the fact that the thing holds for all posterior distributions. We can choose mu to optimize this bound. Okay, so that's the form of the bound. And I just wanted to show you some performances that we've obtained on some simple data sets, but just to give you a flavor of the quality of the bound that you can get. So these are the data sets. And what we've applied here is twofold cross-validation, tenfold cross-validation. So we're also using the bound here to do model selection. So this is the pack-Bayes bound that I've just shown you. And this is the actual bound that you get. And this is the performance you get when you do model selection over the kernel width and the C parameter, the regularization parameter, the performance that you get compared to the performance you would get using tenfold or twofold cross-validation. So first, I think several things to observe. Firstly, the model selection is doing, in many cases, as well or even better than tenfold cross-validation. So here, slightly better. Here, not insignificantly better. This case, very slightly worse, and this case, very slightly worse. But certainly very competitive across all of these data sets. As I say, they're all quite small data sets. They're all, standard, UCI data sets. But the other thing to observe is actually that the bounds are surprisingly, well, maybe not for you, but for me, surprisingly tight and realistic. So in this case, this is just a factor, less than a factor of 3, 2.5 roughly. Here, less than 2 even. Here, maybe bigger, but a factor of 10 or so. And here, as you see, a reasonably small factor. So these are, real bounds that are actually delivered by this procedure, and they're reasonably tight, and they are driving reasonably good model selection. So I think, there's this idea that I just want to sort of break this kind of idea that SLT, statistical learning theory, is doing worst case bounds and they're not practical. In this case, they certainly, are practical, and they are delivering reasonable performance. I also just want to highlight, this is, I haven't, done shown you what is involved here, but this is basically using half the training data to learn a prior, and then using that in terms of the KL divergence, and so you can actually get tighter bounds, and in every case, quite significantly tighter bounds. But interestingly, the model selection performs less well in most cases. Okay, in this case it's similar, in this case it's quite a bit worse, in this case it's slightly worse, and in this case it's quite a bit worse. You can actually then turn that into an algorithm which actually optimizes this bound that would be given by the sort of KL divergence between the prior now, nuanced prior that you've learned from half the data. You're still using all the data for training, but you're just using half the data for the prior, and therefore your bound only depends on the second half of the data, but you still can train on all of the data. These are two versions, but if I look at this one, look at the tightness of these bounds, 0.047. Okay, again, model selection is not performing well. In this case, it happens to be the best, but the actual bounds are really significantly tighter in many cases than, say, this one. So it's kind of ironic that you're getting better bounds but worse model selection. Anyway, I think the main take-home message I wanted to say is the bounds are surprisingly tight. They can drive model selection, but there's not always a good correlation between the tightness and the quality of the model selection. Okay, so I'm now going to move on to say just a few points about the relationship between packed-Bayes bounds and Bayesian learning, which will also inform some of the work that will be presented later. So firstly, let's think about the prior. So in packed-Bayes bounds, we didn't have to say anything about the prior being true or not. There wasn't any sense in which all we had to know was the prior was defined before we saw the data. So the bounds still hold even if the prior is wrong. Obviously, there must be some cost, and the cost will be simply in the quality of the bound that is given. If you pick a very poor prior, you may get weaker bounds as a result. I contrast that with the Bayesian inference, in which there's some difficulty in that you would need to assume that the prior is correct in order to have some confidence that the inference was correct. So there's a sort of difference in quality of what's going on here in relation to the prior. If we look at the posterior distribution, again, there's a difference. The packed-Bayes bounds, as I've emphasized, they hold for all posterior distributions. But Bayesian inference would like you to, it can only really say anything about using the posterior computed by Bayesian inference. Of course, there are approximations, and those are nice to do and work in practice, but there's a little bit of a mismatch between what the theory is saying you should do and what you're actually doing. But in the packed-Bayes case, that's no problem. You can use whatever posterior you want. Again, it will simply affect the quality of the bound. But what you trade here is ability to compute the bound with the quality of the bound. And finally, the data distribution. The packed-Bayes bounds, there's a kind of twist here that's quite interesting, and we'll come back to, in that the prior can be defined in terms of the data generating distribution, provided it doesn't depend on the particular sample. And you might say, well, wait a minute, if you define it in terms of the data generating distribution, you don't know what that is, so how can you don't even know what the prior is. But if you look at the packed-Bayes bound, the prior only enters in that KL divergence term. So what we can show is, in many cases, if you can upper bound that, in other words, estimate that KL divergence from information you have about the prior in the way it's defined, the fact that you don't know the prior doesn't matter. So it's a kind of interesting, sweet trick, okay? So we'll show you some examples of that. So in the Bayesian inference, the data distribution actually only enters through the noise model, generating the output. So effectively, the input part of the distribution does not arise, which, you know, can be seen as a strength in some sense. So I don't want to, I'm not implying any criticism there. It's just, you know, a difference in the way it applies. Okay, so I'm kind of drawing to a close of this second generation. I think it leads to practical algorithms, and as I said, even practical model selection. It motivates and explains, I think, known heuristics, which is nice, kind of it accords with those. The proof techniques are refined and, you know, have gone through a number of iterations, let's say, which I think are also interesting, and have led to significantly tighter bounds. So I think there's, you know, quite a rounded story here. But I think where, you know, we are now is we're actually seeing this very impressive performance from deep learning, and many of these techniques are unable to provide, let's say, appropriate bounds explanations for the performance of deep learning. And for that reason, I think we may need a next generation statistical learning theory at this point. So I'm going to hand over to Omar to take you into hyperdrive on the Hitchhiker's Guide. Thanks.
Anyone heard of this thing called deep learning? So it turns out deep neural networks have faced some sort of a challenge, you know, when one thinks of statistical learning theory. They show pretty good performance, despite the fact that they deal with function classes of, you know, very complex function classes. Something that came up while John was speaking was this relation, this connection between the margin and the accuracy with which one has to estimate the weights. So think of the output of a neural network, the weights output by a neural network. If those weights somehow live, you know, in a region, in a wide region, sometimes it has been called a flat, wide region with good generalization, then that's some property that has been connected to the ability to generalize. We would like to point out here that in the pack-based approach, once you throw in randomization, so if you do have this kind of output from your neural network, you know, weights that live in a wide region of good performance, thrown in randomization, it seems that performance, it's unlikely, it's unexpected that it will go any worse. It's quite to be expected that it will actually be better. I found this thing about randomness fascinating. It seems that randomness has some sort of smoothing effect, but that's more like a personal note. Suigaite and Roy have derived useful bounds in this way. And there have also been suggestions that stability of stochastic gradient descent leads to good generalization. What we're going to do, or what I'm going to see in the next few slides, 5 slides left after this one, by the way, is we're going to present an approach that combines stability with the pack-based framework that you just saw John describe, and argue that this make a connection with a learning principle that somehow draws from information theoretic principles, and point out some possible directions of research. So let me first talk about stability. I like to describe it, so what's shown in the slide here is capital A is my algorithm. The argument for capital A is a particular realization of a sample. Let's say that we're looking at a fixed sample size, M. And now I want to see if I feed different samples to my algorithm, how different can the outputs be? That's the basic idea of stability. Somehow measure the difference between the outputs of my algorithm when you feed it with different training samples. So in order to make this a little bit more precise, and just to clarify notation 2, the arguments are n tuples. And to make this statement mathematically precise, let me say that the algorithm has uniform hypothesis stability beta. Beta is a coefficient, the factor shown in the left-hand side, at a specific sample size when that inequality is satisfied. So I would like you to think, that the algorithm outputs elements of a norm space. That's how it makes sense to talk about the norm difference between the outputs based from two different training sets. So these kind of models, cases where your algorithm outputs a weight vector, this applies to SVMs, more generally to RKHS, this applies also to neural networks. And the property of sensitivity, or the property of stability, I like to see it as a property of smoothness of the output of the algorithm. In fact, it's a Lipschitz factor. If you look at the left-hand side, on the left-hand side, you have the Hamming distance between the two samples. So how different can the outputs of the algorithm be on two different training sets? If my algorithm has stability beta, never mind about, if we know that the algorithm has stability beta, then that difference can be at most beta times the number of entries in which the two samples are different. This is not the only case in which stability has been studied. It has been studied through the lenses of a loss function. This is a little bit, in a way, it's you can call it a little bit more general in that it covers cases, not only cases where the output lives in a space with a special structure. So the reason stability study, and I'm going to show this in the next slide, is in connection with obtaining generalization bounds, the topic of the whole tutorial. But I want to point out that this particular notion of uniform stability, either uniform stability of the hypothesis or through the loss function, is a worst-case notion of stability in the sense that it is data insensitive, it is even distribution insensitive. Its definition has nothing to do with the Jetta-Dreyfus distribution. And it is kind of like an ongoing topic of research, keeping in mind a good thing to look at, how to bring in notions of stability that capture something more about the data. So how does stability come in for generalization? I just want to show you the form of bounds based on stability. If you have an algorithm that somehow you have obtained an estimate of the stability coefficient for that algorithm, then you can get a generalization bound for that algorithm, more or less of this form, where the true risk is bounded from above by the empirical risk plus a term that depends not just on the sample size and the confidence parameter, also on the stability factor. One thing that I want to emphasize here, why do we care about generalization bounds? So the goal should be to put a leash on the true error. The goal is to have a small true error. The problem, the true error is not a computable thing. We don't have access to the true error. This is something that has been, I hope it is something that has been mentioned a few times, that it is sinking in. So given that that is the case, it makes sense to aim for minimizing upper bounds on the true error. If we minimize upper bounds on the true error, then we're guaranteed to put the true error on a short leash. So minimizing expressions of the form on the left-hand side of this, on the right-hand side of this inequality makes a lot of sense. Minimizing just empirical risk doesn't make a lot of sense to me, because the empirical risk by itself is not an upper bound on the true risk. Minimizing some cooked up formula involving the empirical risk doesn't make much sense unless there is very good indication that such a thing is an upper bound on the true risk. So this is why we care about upper bounds on the true risk. This is what we care about generalization bounds. By the way, the notion of stability that was just mentioned, it was introduced by Bousquet and Elisif, and a few comments. So the idea is that if individual examples do not affect too much the output of an algorithm, then the output of the algorithm should be somehow concentrated. This can be applied to kernel methods where the stability coefficient can be estimated, and it is related, in fact, to the regularization factor, although those bounds are rather weak. And a question is, if we know that the output of an algorithm is highly concentrated, can we do better? Can we obtain better generalization bounds? Just kind of like to set the stage for the next slide, I'm going to mention something about distribution-dependent priors. This is an idea that was introduced by Catoni back in 2007, if I'm not wrong. He looked Gibbs or Boltzmann kinds of distributions. So for a prior, he looked at basically the normalized exponential of the true risk, and for a posterior, exponential of the empirical risk. Notice that the posterior is something computable from data. The prior does not depend on sample data, although the prior does depend on the data generating distribution. In a sense, it is non-computable because we don't know the data generating distribution. But as John was pointing out, in the pack-based framework, that is okay, since in the end, all that you care about is how far is the posterior from the prior in terms of the KL divergence. So as long as you're able to control the KL divergence of posterior to prior, then you're doing good, even if you don't know explicitly, even if you cannot calculate explicitly the prior. But so the point of this, so look at Q0, is defined in terms of the risk, is defined in terms of the data generating distribution. That's the idea that was introduced about how to bring in the data generating distribution to form priors for the pack-based framework. And here is an example of a pack-based bound on the KL divergence of average empirical risk to average true risk. Of course, once you have a bound of this form, you can invert it. You can invert the KL divergence to get a bound of the average true risk. That's that. So I'm going to try to give you a little bit of an impression for what stability combined with pack-based framework can do. If you have an algorithm that has uniform hypothesis stability, so somehow you know that that property is satisfied for your algorithm, then for a given sample size, you have the following bound. The KL divergence between the average empirical risk and the true empirical risk is bounded from above by a quantity that depends on the stability coefficient besides sample size and confidence parameter. How this bound is obtained? It was obtained using Gaussian randomization, with a prior being a Gaussian center at the expected weight vector output by the algorithm, and a special covariance structure. And the posterior is a Gaussian center at the actual random output of the algorithm, same covariance structure as the prior. Using Gaussians, then, one controls the KL divergence. I mean, the KL divergence between two Gaussian distributions is computable explicitly. And this is how, in the end, we care only about the norm distance between the random output and its expectation. This is how, in the end, a concentration inequality comes in. And so those are the main components of the proof of this bound. First, the typical pack-based bound, which says that to bound the KL divergence between average risk, empirical and true, you need to bound the KL divergence between posterior and prior. And we bounded that in view that we were using Gaussian distributions, we bounded that by using a concentration inequality for the output weight vector from its expectation. Just in case that you're wondering, the norm being used is the RKHS norm. Last but not least, there is some tools coming in from information theory that have been used by Achille and Soato to somehow capture the idea of how much information about the particular training set is stored in the weight vectors learned by a neural network. The idea is that overfitting, that thing that we learn to kind of avoid, is related to think that your weight vector stores too much information about the particular data set, then that's what we call overfitting. Ideally, your weight vector stores information about the data generating distribution itself, then that's when we have good generalization. So storing too much information in the particular learned weight vector is kind of like a way of weakening the concentration of the weight vector. And the argument is that something kind of like based on the informational bottleneck principle that Achille and Soato come up with a specific function to minimize that. Then if you use the bound minimizing algorithm, the output is a weight vector that stores minimal information about the particular training set in a sense that they made specific. This could potentially lead to tighter pack-based bounds. This is something to be studied. This is something to be seen. And with that, I'm closing the tutorial. So statistical learning theory, we say that it might be offering a nice hyperlift. Put the thumb up you go, sometime soon, kind of, ish. Thank you very much.
So I guess we have some time. No, don't run away yet. Don't run away yet. We have some time for questions. In case there are any questions from the audience, we have 10 minutes.
John did promise.
Are there any questions?
Also, John did promise that we would have some references for you. These are at the back of the slides. So if anyone wants to see them, they are available.
Yeah. So I guess there are some questions from the audience. So yeah.
Yeah. Do you listen to me? Yeah. Hello. I have a question with respect to the stability plus back bias bound. I think that actually it doesn't converge to zero when n goes to infinity. I don't know if you can go back to the slide.
So it would be nice actually if you could wait five minutes. So we're waiting for some slide to come up.
I wasn't sure. Okay, I think you can ask, yeah. So please ask question, yeah.
Oh, yeah, so in the slide where you have the stability plus the pack bias bound, the generalization bound, there is one term that depends linearly in n. I think it's n beta square times 1 plus log over 1 delta square. But if you divide that by n, that means that the bound doesn't go to 0 as n goes to infinity, right? What's the meaning of that? It has to do something with the prior on the function space, on the hypothesis space?
So, as I understood, maybe I can repeat back what you were saying. The beta would be dependent on n or the sample size potentially. Right.
I see.
So in practice it is, but not as strongly as that. I mean, in our experience of applying this bound, we have actually, generated the actual rate of increase of beta is less sharp, and you actually do generate. What we are not so happy about is the fact that as you raise generally the regularization, this does become weak. And we believe that is as a result of too much, there's sort of if you like, a uniform bound on the stability, which doesn't take into account the specifics. So it's a bit like, our VC thing. This is like VC for stability. We need to have a more nuanced understanding of how stability actually operates in a particular case.
I see.
So that's, I think,
I see. Okay, thanks.
Key question.
So there's one more question. It would be really nice if everybody else could try to be quiet, just for the time that the question is asked.
Yeah, hi. So thanks for the great talk. So in the beginning of the talk, I think the first generation, right, there was some criticisms that the bounds were not realistic for real data that you see in real world settings, right? And so you worked, to make them more tight. But then now that we have this, all these adversarial examples popping up, potentially maybe those original bounds are actually, they are doing what you would expect to see if you consider adversarial distributions, which according to this morning's tutorial are abundant and they're all over the place. So just wanted to hear what your thoughts are on kind of these other adversarial distributions that supposedly are realistic in the real world.
So just to repeat what I think you were asking, I mean, were you asking about the problem with, let's say, adversarial inputs into a deep network and the fact that they can be used to actually cause the network to make an error, or you're just thinking generally adversarial situations where you don't have IID data, but you're having bounds that are somehow worst case over all possible inputs?
More of the former, where...
The former?
Yeah, so the data, the inputs have been manipulated to to increase the error.
Yeah.
Right, and so and some of the bounds that were shown were quite large if you consider adversarial examples, which I think reflects those early bounds.
So yeah, I mean, these bounds based on IID data, the chances of you hitting those adversarial inputs are so low that the fact that they make an error will not appear in, will not affect these bounds. I think we would need to have a much more, I think the key there will be learning properties of the distribution. So in some sense the manifold, which is, I think, the key to, if you like, the difference between those errors that are made, through sort of pointing very slightly differences, as opposed to perhaps understanding some structure in the data, which would, so for example, in an animal, you would identify eyes, you would identify the type of fur, you would identify a number of factors, and you'd have to cause errors in all of these factors in order to make an error in the classification, rather than just, somehow some gestalt of the image that is used in the deep network case to do the classification. So I think it's more about the way to approach that problem is to try and pose the problem as a learning problem about structure in data rather than just as a classification problem per se. But I think, that doesn't mean SLT wouldn't have a role to play in doing that, but I think it would be a more structured role in learning different sort of elements, if you like, of the structure of the input.
Okay, thanks.
Thank you.
Are there any more questions for the speakers? Yeah.
So regarding your last slide, could you elaborate a bit more on this information and how information complexity and how it can be used to optimize the bound on the...
So the argument made, this isn't, obviously our work at Kili and Suato have looked at this idea of measuring the amount of information in the weights. So that obviously the information in the weights has two sources. One is the underlying distribution, but then there's also the question of whether, given the underlying distribution, is there more specific information about the actual training data that was used? And the point they're making is if there's too much information about the training data as opposed to the underlying distribution, that implies some sort of overfitting. They make the argument that actually stochastic gradient descent, and particularly the information bottleneck, does in some way control that, but not in such a specific way that that it might, that there could be criteria you could use that would actually help you to control this more tightly than perhaps, it's sort of almost a byproduct of the sort of information bottleneck training that is frequently used with stochastic gradient descent. I think there's also this possibility there's a relationship with differential privacy and the fact that you introduce randomness, and so the specific information about elements of the training set get lost and are not encoded in, so there's a connection there potentially as well. So I think these are all ideas that we believe could be used to in some way improve the bounds on concentration that you get, which will then improve the bounds on the generalization, because these depend on the concentration, if you like, of the actual weight vectors you observe relative to the expected value of what you would observe over a set of random training sets. So that's the idea, but as I say, it's quite vague at this stage, but it's I think an intriguing approach, and I kind of was feeling this is actually potentially a new way of thinking about generalization, which is different from the margin or the sort of region of weight space. I think margin and region of weight space are very similar. In some sense, there's room around the solution to do similar stuff, and you kind of, if that's a lot of room, then you kind of almost divide the total complexity by the complexity of that space, and that gives you some sort of quotient, which would be the complexity of your algorithm. Which I think, but I think this is different in some sense. So that's the, I think, intriguing direction. Okay, thanks.
Any more questions? If not, let's thank the speakers again.
Okay, thank you.